The question says a uniform bar with a weight of 20 Newton rests on two supports P and Q as shown, and weights are suspended as shown in the figure below. Calculate the reaction at P and Q on the support. If you look at this question, we need to understand the question before we begin to solve it. If you look at it, the bar has its center of gravity at 20 Newton. That means the weight of the bar is acting at 20 Newton, and the bar is being supported at two different points. The bar is because it is being supported, it balances horizontally, which means it is in equilibrium. But there are reactions at these supporting edges. That is at point P, and at point P there are some reactions there. So the reactions are the forces that are acting vertically, because all these weights are attached at this point. They are acting downwardly. So there must be some reactions that must be equals to the weight, to this weight that are acting downwardly. What that simply means is that for all the forces, when a body is in equilibrium, all the vertical forces acting, that is the reaction, are equals to all the forces, all the downward forces. What that simply means is our x plus y, which are the vertical forces, those forces that are acting upwardly, are equals to all the forces that are acting downwardly. That is the 15, 20, and 5. So we have 15 plus 20 plus 5. That means our x plus y is equals to 40 Newton. Another thing we need to look at, let's call this one equation 1. Another thing we need to look at is to resolve this, for the moment. Find the moment of this particular bar. So you can find it at any point. We can assume point P or assume point Q as our moment, as our point of reference. So if you are to use point Q, for example, let's assume our bar is going to rotate at point Q. That means we are resolving the bar at Q. So what that simply means is that we are assuming this P does not exist. So we are assuming the P does not exist, that is, the meter ruler exists without this point, without this particular point. That is, let's assume we are removing this particular knife edge from the diagram. So which means the only one that exists is this. So what that simply means is that this body is going to rotate. If we remove this particular knife edge, it's going to rotate. The body is going to rotate. And this particular force, if you look at this particular force, it's going to rotate the meter rule in this direction. If you imagine you attach a weight at this point to a diagram like this, it's going to pull the meter rule in this direction. The same thing we did. This one too is going to pull it in that direction. It's going to pull the meter rule in that direction. But a weight you attach at this point will pull the meter rule in this direction. In this direction like this. Anything you attach to it will move meter rule in this direction. But the weight here is going to rotate it like this. The weight here is going to rotate it like this. Then let's look at this. This point X. Let's assume you tie a rope at this point X and you are trying to pull the meter rule. It will pull the meter rule like this in this direction. So at point X, we have our direction looks like this. While at point Y, the point Y is not going to exist because it is directly above our fulcrum. So the point Y cannot exist because it is directly above. It is directly above the fulcrum. So point Y would go. So let's resolve. So these are the four forces that can rotate the meter rule. This can rotate it. This can rotate it. This can rotate it. This can also equally rotate it. But why? No. So we have, if you look at this one, so this and this, they are going in the same direction, while this and this, they are going in the same direction. So this is our anti-clockwise forces, our anti-clockwise moment rather, and this is our clockwise moment. If you look at the distance of this, if you look at distance of 5 to the point of fulcrum, we have just 2 centimeters. So our clockwise moment, let's say it is equals to our anti-clockwise moment. So our clockwise moment is 5 times the distance, the perpendicular distance to the fulcrum, that is 2, plus this one is also a clockwise moment, like this. It is moving like this. This is where it exists. So we can say plus x times, let me use dots so that I don't mix them up. X times, we have here, we have 2 centimeters, we have 3 centimeters, so it is 5 centimeters to the fulcrum. So that is x times 5 is equals to, then we have the anti-clockwise moment. This is 15. This will be 15 times, if you look at the distance to the fulcrum, it will be 3 plus 2 plus 3, that will be 8. So we have 15 times 8 centimeters plus, this one is also going in that direction, so we have 20. So we have 20 times its distance to the fulcrum, which is 3 centimeters. So here we have 10 plus 5x equals to 15 times 8. 15 times 8, that will give us 15, here we have 40, 0, that will give us 120. 120 plus, this will give us 60. So we have 5x equals to 180 minus 10. So that means our x is equals to 170 over 5. 5 here 1, 5 in 17, that is 3. 5 in 20, that's 34. That's 34 Newton. So if our x is 34 Newton, it means that our y will be equals to 40 minus 34, which is equals to 6 Newton. And that is the final value of these forces. And if you look at it, this is 34 plus 6, that gives us 40. If you look at this, the downward forces, it's also, all the downward forces, the addition of the downward forces is also 40. That is 15 plus this, it will give us 40. That's another way to check that our answers are right. Thank you.